Hello everyone. In this video, we talk about using matplotlib for data visualization and plotting. Matplotlib is perhaps the most widely used library for creating static and interactive plots in Python because it provides a versatile and comprehensive set of tools for various types of plots. This includes line plots, scatter plots, bar plots, histograms, and so on. And therefore, in this video, our goal is to show you the basics of using matplotlib. And so once you learn this basic, you will be able to apply them to different types of plots that you may need based on your application. And the nice thing about matplotlib is that you have complete control over the appearance of plots. For example, customization of colors, styles, labels, and annotations, as we're gonna see in this video. In order to use matplotlib, the first thing is to import this library. Since we talked about modules and packages in the previous video, we have here this matplotlib package or library. And inside this, we have a module, which is called pyplot. And therefore, the goal here is to import this module from this package or library. But it is very common to also use an alias. And here we import this as plt. So therefore, we really shorten this name that we have here to make it much easier later on. So plt refers to this module. And then we say plt. And one of the things that you will definitely need is plt.plot. And this is what is known as the line plot. And here we give a list of 5 numbers. And we also specify the marker type. We're going to talk more about marker type, but for now, it kind of makes sense that these are the markers that we're going to use to plot these data points. So let's run this cell and see what we get. And something before I forget is that you also have to use plt.show to make sure that you actually show the plot that you have. So this is something kind of like, important, kind of like, when you're using print and then some string to make sure that you print that string, that's kind of like a similar thing when you're using matplotlib. And so you can see that here, now we have these 5 data points that we have, 10, 20, 30, 40, and 50 on the y-axis or the y-coordinates of these 5 data points. But the strange thing is that the x values are 0, 1, 2, 3, and 4. So you may ask how we got these numbers here. So remember that when you're using plt.plot and provide, let's say like here, a Python list, what really happens in the background is that your x values are the indices of the elements in this list, right? So we have these 10 through 50, but we know that the indexing in Python starts from 0. So the first element is at index 0, then index 1, 2, 3, and 4. And plt.plot assumes that the x values are these indices. However, if you want to provide a different set of x values, you completely have this option to provide 2 lists. And so this really, I would say, makes much more sense because now you have one list where you get the x coordinates, and then you have another list where you get your y coordinates. So this is very intuitive, the way that we actually, plot 2D data points on a piece of paper, right? So we see that for the first point, the x value should be 1, the y value should be 10, and that's exactly what we see here, 1 and 10. And then for the second element, we have 2 and 20, right? So we get 2 and 20. And in this case, we obviously can change these lists however we want to get different set of x values. So we have the option to change both x coordinates and y coordinates. Okay, so now we learned the basics of plt.plot for line plots. Now, let's talk a little bit more about customization. So one of the things that we can use is plt.access function in matplotlib, which is used to set the axis limits for the x and y axis of a plot. And so the general syntax is that we say plt.axis, and then we provide a list where we have xmin, xmax, ymin, and ymax, right? So these are the min and max values for each axis. So we're going to have the same plot that we had before. And let's say in this case, for some reason, we want to make sure that the x values that we show on the plot are from 0 to 6, and the y values on the y-axis are between 0 and 60. So if I run this right now, you can see that on the x-axis, we have 0 to 6, and on the y-axis, we have 0 to 60. In this case, obviously, it makes more sense to set this the minimum value to be 1, because we don't have any plot for anything less than 1. And the same thing for the max value to be 5. And for y-axis to be 10 through 50. And if you run this now, you can see that we get a really nice plot where we do not have any empty spaces, right? So that's why one of the reasons you want to use this plt.axis. If you have some empty spaces around your figure and that's something you don't want to have, then you can make sure that you can manually adjust the min and max values for each axis. And this is the syntax to perform this. Okay, so now let's go to the next step. Let's say we want to plot a quadratic function. And in this case, a quadratic function is y equals x squared, right? X raised to the power of 2. The first thing that you need to do is to define a grid for the x-axis, right? So in this case, x is technically your independent variable, and we are using np.linspace to have 500 data points equally spaced from -2 to 2. So obviously these are the x min and x max. You can adjust them as you want, but in this case, we want to have a plot from -2 to 2, and we have 500 of these data points. And then in the next line, we're gonna raise each x to the power of 2 and store the results in this numpy array called y. And therefore, when you want to plot this, remember the x values are given through this np.linspace. So this is the independent variable. And then the y is x squared, which is the dependent variable. And you use the plt.plot. There are also some other options you can use for customization, such as giving labels to axes. So plt.xlabel. This shows this string as the label for the x-axis, similarly for the y-axis. And also we can even use plt.title to put a title above your figure. For example, here saying that this is we're plotting a square function, which is y equals x squared. As we said before, we can use plt.axis. We know here that the x values are from -2 to 2. And since we know that we use, the x squared function, so the y values are also from 0 to 4, right? So we don't get any negative numbers because we are using this quadratic function, but the max would be 4. And if we plot this right now, so you can see that on the x-axis, we have values that are from -2 to 2. And then we have on the y-axis from 0 to 4. You can see the labels here. You can see the title here. And this is definitely the quadratic function that we know. If you want here, you can also use marker to better see the data points that we have. Obviously here, it's hard to see them because we have 500 of them, so they're very, very close. But if I use that, you can see that now this looks much thicker, this curve, than before, and that's because we have all these markers that are so close to each other. So for example, I can decrease the number of data points to 10. And if I do that, so you can see that now how this works. But this doesn't look very smooth because we only have a few data points, right? So you can always increase these, let's say 20. So this should a little bit better, and so on. So now you can see that we have all these XY coordinates that this line plot connects them together to get the shape of this x squared function. We can also add more customization. One of them is using this option called line style, and the other one is color. So here we have the documentation for both of these customization options that we have. So you're more than welcome to look at them and figure out different options that you have. But as you can see here, one of the things is to set the line style. And I set that to be dashed. So this is going to be a dashed line. And also the other one is color, right? So there are multiple options for color, like red, blue, green, etc. And also like before, we have the labels for axes and the title. And you can see that when I plot this right now, so you get this dashed line and the color is red, right? So if you want to change this, let's say color to green, you can do that, or blue. So this gives you a lot of different ways to customize this. And as you can see, just to make sure that you see this, since here for this plot, we didn't use plt.access, you can see that we get some empty space below this sort of curve, and also for values more than 4, right? So if you want to get rid of that space, we can use what we had before by providing those limits, right? So we say that for x, we have -2 to 2. For y values, we have 0 to 4. And if you run these, now you can see that we got rid of those empty spaces. So this is sometimes preferable because you want to make sure you have very nice figures. And then the other thing is about the marker type, right? So this is something that you have seen. This is the way that we represent these 2D coordinates or data points, but you can choose different types of markers. So far we have been using what is called O, that represents a circle, but also we have other options too. So if you use S, that stands for a square. If you use uppercase D, that stands for diamond. You can also use this notation for upward triangle, so you can customize this as you desire. So here we use S, so you can see that we have these S squares. But I can use, for example, this upper triangle if I want to. But I'm gonna move this back to a square. And something also to keep in mind here, I can take this to the next line that you can see. You also have an option for marker size, right? So if I use 50 instead of 5, you can see that now these markers are huge. Let's put something more reasonable. So I put like 10, right? So now you can really see these markers very well. But depending on application, you might want to choose them a little bit smaller. But you have a full control over all these options. The other nice thing about matplotlib is that you can have multiple plots in one figure. And in this case, you can visualize all of them inside one figure, which can be very helpful when you want to save a space. So let's look at this example that we have here, that we have these x values that, like before, we have from -2 to 2. And in this case, we define 3 functions. One is a linear function, 2x plus 3. Then is a quadratic function, x squared plus 2x plus 1. And then we have a cubic function. And so the way that you can have multiple plots in one figure is that use this plt.plot as many times as you want with different set of xy coordinates, as you can see here. But in this case, something which is very important and recommended is to use this label argument, where you provide a label for this plot. So the first one is linear, the second one is quadratic, the third one is cubic. And now, like before, we can add X label, Y label, title, but something which is very important in this case is to include this plt.legend. And if I run this cell, we can see that now we have these three plots, and we have this box here. So this is what is called the legend, which has the information about those labels that you provided, like linear function, quadratic, cubic, right? Linear function, quadratic, and cubic. Therefore, in this case, it's always important to provide these labels. It's not mandatory, but otherwise it's impossible to figure out which plot corresponds to which like function here, right? So you need to provide these labels. The next thing that we're going to talk about is how to save a figure in matplotlib. And in order to do that, you can use plt.savefig function. And there are two things that you need to provide when you're using plt.savefig. You need to provide the name for this figure that you are saving, right? That's very intuitive. And then the other one is this DPI, which stands for dots per inch. And this really determines the resolution or quality of the saved figure by how many dots or pixels should be used per inch. So the higher the DPI, the higher quality is the saved image. So like before, we create these X values from here, -5 to 5. We're gonna find the corresponding Y values using this quadratic function. We're gonna, even in the case of one plot, you can add the label and plt.legend, right? So that you don't necessarily have to have multiple plots. You can do this only with one. Something you can always use when you're saving your figures is use this plt.height layout. So it is very hard to exactly characterize what this does, but it improves the overall layout or quality of the plot. So you make sure that all the empty spaces and everything else looks nice. And so that's something that also recommended to use. But the point that we want to make here is this plt.savefig, where you provide the name of the file that you want to use to save this figure, and then use the DPI. So usually you want to have DPI more than 300. In this case, I'm using 600 to have even a better quality image. So you can see that in this case, we have our quadratic function as expected. And now if you look at the current directory or folder that you have, you should be able to see this PNG file. So please make sure that you look at the current folder directory to see whether you have this file or not. So it should be something called, in this case, this name.png, and you can also try to use different DPIs to see the difference between their resolutions. Okay, let's talk about more customization. So the other thing you may want to do is to adjust the font size. So one of the things that you can do is to globally change the font size. That's done using plt.rc_params. And here you set your font size to anything you want. You also have the option to do this, for each individual like customization. For example, for the title, you can change the font size. For X label, Y label, legend, so you can manually change the fonts if you want, or just change the font for everything in your figure using this global font size approach. You can also adjust the figure size that you have using this plt.figure, and you provide this fig size where you have the width and height of your figure. Just to show these points, so you can see that here we have this plt.figure to set this figure size to be width 5 and height 4. And then the other thing also that we have here, we are using these font sizes here, right? To give them different font sizes for the title, X and Y label, etc. So if you run this, so you can see that now we have a figure that looks overall in terms of its width and height is smaller than what we had before. And that's just because of this line. So you can see that if I, let's say, change this to 3 by 3 and run this, now we get something even smaller, which is probably too small for these font sizes that we have here. So let's put this back to 5 by 4. So now you see that the overall dimensions get a little bit bigger. And you can also change these font sizes. So if the title is too large here, we can set this to be something very small, like 10, right? So you can see that now the title, which is this one, is a small. So let's put this back to some other number. You may see that, oh, the legend is too large. So we can adjust that, right? So now the legend is small. So you have the option to change all these font sizes depending on this overall size of your figure and also other requirements. Now let's look at subplots. So for subplots, it's very important because sometimes you may want to have multiple plots in one figure, and sometimes you want to have multiple plots next to each other. Like you can create a grid where you have, let's say, a 2 by 2 grid where you have 4 figures and each one in one of those locations. And in order to do this, the most common way of doing this is using these plt.subplots, right? So this is the first time that we are moving away from plt.plot, right? So now we can use plt.subplots. And the syntax is easy. So you need to have the number of rows, number of columns, and optionally, you can provide the figure size or fig size. Obviously, you can change it later, but you can also adjust it right away. And in this case, what we really want to work with is this axis. So as we say here, this is kind of like a NumPy array, which has this indexing system that starts from 0. So let's see how this works in practice. Let's say you want to create a grid of size 1 by 2, so 1 row, 2 columns, to have these plots individually next to each other. So in this case, we can change the font size that we discussed. But what's really important is that once you create this axis, now you can have axis 0. So this shows you the first place that you have in the grid. So right, we have one on the right, one on the left. So this is the one on the left. And you can use now axis 0.plot and provide the XY coordinates. You can also give the label. It's a little bit different in terms of the way that we provide X and Y labels, right? So before we said like plt.x label, now here you say it's set_x label. That's like a minor difference, but this is just something that you can always just remember, like the difference between subplot and a regular plot. Some of the things are similar, like that legend to show you this label that we have here. And then for the second plot that we have here, the one on the right, now we can use this axis 1. And so now we plot the linear function, etc. And if I run this cell, you can see that now we have 2 plots. So it's a 1 by 2 grid, 1 row, 2 columns. The one on the left is the quadratic function. So this shows you what, how we get this quadratic function. And then for the one on the right side, or the second position, which has index 1, now we have our linear function. So this depends on the application, whether you want to create a grid and have multiple plots individually, or you want to have all these plots in one figure, right? So it really depends on your application. And the nice thing here is that you can really choose any number of rows and columns. Okay, so in matplotlib, you can also draw text on your plots to add more information. This is something very important when you want to convey some important message. And one of these options is using plt.text, which is very simple to use. You provide the XY coordinates of where the text you want to be placed. S is the string that you want to show. This is the text string. And you also have options like font size, color, the horizontal adjustment, vertical adjustment, etc. So those are optional arguments. But just to show you how this works, so let's say we have this line plot where we have these x values, we have these y values. Obviously, the maximum value happens at this point where we get 20 for the y value and 3 for the x value. And so if I run this cell, you can see that we have our normal plot, right? So we have our x-axis, we have our y-axis, and this is where the maximum y value happens. And you want to show this text, which it says max value. So in order to do that, that's the code that we're going to use. So we're going to say plt.text. We want to choose the x value to be 2.6, right? Because we don't want to put this like a string right on this point. We want to be able to see this. So we put this at 2.6, and the y value is obviously a little bit less than 20, so it's 19. And this is the message that we want to show. So if you want to change this, you can, for example, add max value 1. So you can see that this one now is added, but we can remove this. You can adjust the font size and everything else. So that's one way of adding annotation or text to your plot. But if you're looking for something a little bit more sophisticated, you can use plt.annotate. And plt.annotate is a function that you can add annotations. And the main difference is that you can also use some arrows to exactly point to the points that you want. So to a specific locations of the figure. And the syntax is a little bit different. In this case, first, you provide the text string to be displayed. Then you want to provide the XY coordinates of the point that you want the arrow to be pointing towards it. And then the XY coordinates for your text. And also you have some options for the arrow that you want to plot. So just to show the difference, here we have exactly the same setup, but we have this plt.annotate. And you can see that first you put your message, XY coordinates for the data point. So here we are trying to have an arrow that points towards 3 and 20, which was like the maximum we wanted to show. The XY for the text, and some information about the arrow, such as like the arrow should be blue and things like that. So you can see now in this case, right, so we get a little bit a better visualization. So we can show that, okay, this is the max value that we are talking about. And, before we just wrote max value next to it. So it wasn't necessarily super clear what point we are referring to. But in this case, it's much easier. Okay, so let's talk about now 3D plots. Creating 3D plots in matplotlib is something we can use to visualize data points in three-dimensional spaces. This is obviously something that we are not going to use as much as 2D plots, but I wanted you to have at least the instructions for creating these 3D plots if needed. And so it's here we have the full instruction, but I can show you in the code the main differences. So one thing that you have to do for 3D plots, you have to add this line. So there is a package or library called MPL toolkits. So inside this, we're going to use this axis 3D. So this is what we need for creating 3D axis. We're going to create the data. So here you need to have 3 coordinates, right? Like X, Y, Z or X, Y, T. So that's how we create it. We use some sine and cosine function, and T is the independent variable. And then very similar to before, we can use plt.figure. And in this case, you want to, once you create this figure and assign it to the variable fig, you want to add this thing called add subplot. And you want to make sure that the projection is equal to 3D. This font is just for the font size, as we know. And then the main difference is that you take this object x and now say x.plot 3D, and you provide the x, y, z coordinates. And after this, everything is very much the same as before. We can set the X labels, you can use tight layout, you can save the figure. And something else that is also important is to use this view init And this shows you the viewing angle. So using the elevation and azimuthal angles of the view, right? So you can really change the perspective you're looking at this 3D plot. So in this case, you can see that we have this nice 3D plot, right? So we have this t variable, and then x and y are defined using sine and cosine. That's why we get this very nice 3D plot here. And if you want, for example, to look at this from a different perspective, you can choose this elevation, for example, to be 0. So now you can see that elevation is 0, and you can increase that to be 20, or even increase that to be 60, right? So now we are going to look at this from above, right? But I'm going to put this at 20. So the full instructions is here that how you should do it, adding this add subplot, then using xplot3d, and also this view in it. The next type of plot that we're going to cover is a scatter plot. So scatter plots and line plots are both used very frequently to visualize data, but they serve different purposes. And the main thing about the scatter plots is that they can be used to visualize the relationship between two variables. And instead of connecting them together, data points here are represented as individual markers. So in this case, you can see that like before, we have a set of x values and then y values, and then we use plt.scatter. We have the xy values. So these are the x coordinates, y coordinates. And s here is the marker size. So before we use the argument marker size, now we use s. And still you can choose the marker type and the color, which is shown here by the c variable. And you can see that in this case, right, so we have one data point which has x value 1 and y value 10, right? So we have 1 and 10. That's the first one. Based on what we see here, the next one is 2 and 12. Let's see if that's correct. Yes, 2 and 12. And then next one, 3 and 8. And you can see that here we are not connecting these together. It's just visualizing the relationship between them. And to see, how this works, especially in the context of machine learning and data science, let's look at a real-world problem, which is known as iris flower dataset. And this dataset has 4 measurements of iris flowers and are categorized into 3 species based on those measurements. And you can see that in this case, in order to access this data, we can go into scikit-learn. Inside scikit-learn, there is a module called datasets. And from that, we're going to import load iris. So this is the way that we can load the iris dataset. And then inside that, we have the actual features for these iris flowers and the target values, and also the feature names. So if you look at this data, once we get this, so you can see that now each data point has 4 features because we have, 4 measurements of each. And then we have the targets for them. So this shows us all these 5 data points belong to class 0. And if you're wondering what those 4 features are, for example, 5.1, 3.4, 5, 1.4, and 0.2, these are the names: the sepal length, sepal width, petal length, and petal width. So we have 4 features or measurements per sample. And this is sample 1, sample 2, sample 3. So that's usually how we store and access data points when we have these types of data sets. But what we want to more focus on here is that if we only select 2 of the features, right? So the feature 1 and feature 2 across all the samples, right? Can we see interesting relationships in the data? So what we do is that we say that we want to look at the first 2 features, which are sepal length and sepal width, index 0, index 1. And then we are also going to distinguish between different classes, right? So we write a for loop so that we have now 3 different scatter plots inside one figure. And the way that we can do this is by putting this condition that each time we're gonna plot only data points with the values of target values that are equal to this class label, which is 0, 1, and 2 here, because we have 3 classes. And then you have the X feature, which is 0, Y feature, which is 1. And also we're going to add this label where we say now this is a species 0, 1, and 2, depending on what this class label is when we have this for loop. So if I run this, so you can see that now on the x-axis, we have sepal length. That's why it's so important to add x label and y label. And then on the y-axis, we have sepal width. And these are the xy coordinates for data points from different species or classes. So here we have 3 species. You can see, for example, we see a clear distinction between species 0 in terms of their sepal width and the sepal width for the other 2 classes, right? The sepal width for the blue class is definitely higher than the sepal width for the other classes. So you can easily now draw a line here to separate this blue class from orange and green. So that's why scatter plots are very important in machine learning and data science. The last type of plot that we're going to cover here is histogram plot. And histogram plot is also very popular for statistical data analysis, which is used for graphical representation of the distribution of a data set. And the way that this works is that we use plt.hist, so that stands for histogram. Usually we provide a 1D array here, and this is the data to be histogram. You can provide a sequence of arrays too if you want to plot multiple data sets, but in most cases, make sure that X is just a one-dimensional NumPy array. And then you can have the number of bins, right? So you're gonna, divide these values that you have, all the values in X, into different bins, and you're gonna count the number of data points that you have in each bin. So you find kind of like a frequency plot. But something which is really cool about matplotlib's histogram, you also have this density option where you can set that to true. So by default it's false. But if you set that true, it actually returns a probability density. And what does this mean? It means that in this case, each bin will display the bin's raw count, like how many values fall into that bin, divided by the total number of counts and the bin width, so that what you get at the end has area under the histogram, which is exactly 1. So this is something very important if you have had if you have seen probability density functions before, because probability density functions, they have this property that the area under them is 1. So that's kind of like a nice way of normalization. And so if you set this density to be true, then the y-axis wouldn't be just the raw count, would be this type of normalized raw count, such that the area under this histogram plot would be 1. So you can find more information here at matplotlib.pyplot.hist. But here we're going to see a few applications of these. So let's, in this case, generate a 1D array using np.random.normal. We know that this is the normal distribution generator in NumPy's random module. Log or LOC is the mean, the scale is the standard deviation, and size is the number of samples that we select. So if you look at data right now, if I run this, you can see that data has 1,000 elements. You can use, for example, .shape. So you can see that this is a 1D array containing 1,000 elements. And so what we do here when you use plt.hist, you provide this data, you provide the number of bins, and I personally like to put the density equals true, because now the nice thing is that the y-axis is this sort of like, normalized version, where still you can see that based on what we see here on the x-axis, we have values. So because we created random numbers from a normal distribution with mean 0, this is definitely centered at 0. And then this is the standard deviation or spread of the data. And you can see that in this case, that if we find the area under this, histogram plot, it should be 1. Whereas if I set this density to be false, right, you just find the raw count. So, right, this means that out of those, 1,000 data points, 160 of them, almost more like 150 something, are from like 0 to whatever this number is here on the x-axis. So I personally like the to put the density equal to true. So in that case, we find a more normalized version. It doesn't matter if this is 1,000 or 500. You get more consistent results, right? Because we do not have a raw count. The other thing you can, for example, here do is to increase the number of bins. So if you see like I increase the number of bins, now we have 50 of these bins here, but it may look a little bit less smooth. So that's why you don't want to increase the number of bins too much. You can reduce it if you want. So you can see that now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 bins. But I think in this case, like 20 looks, relatively nice. If, for example, let's say I increase the scale or the standard deviation, we expect that the spread of the data should be also increased. And you can see that that's the case because now when I use a standard deviation 10, these numbers can go from as low as -30 to almost 40, right? Whereas if we set to 1, like before, you can see that they're from -3 to almost 4. So that's something that you can use. Obviously, there are some other options here too, like the color, the edge color. You can see that here the edge colors are black, alpha, right? So this is something, as you make this closer to 0, you get more transparency. And as you get it closer to 1, it gets kind of like darker. So that's something you can adjust as you wish. So that's the histogram plot, but let's do something interesting here. So for example, for the normal distribution, we actually know the probability density function. And that's something that is already inside this library or package called SciPy. So SciPy is similar to NumPy, but it has some more functionality and statistical methods. And inside scipy.stats, right, so that's the module, we have something called norm. And inside this norm, you can use this method or function called PDF, which generates the PDF, right, for the normal distribution with a given mean and a standard deviation. So what we want to do in this case, we want to create our data from this normal distribution, and we sample 1,000 of them. We use plt.hist to provide a histogram, but now we also want to plot the PDF or probability density function of the normal distribution for comparison to see how consistent they are. In order to do this, we're going to use np.linspace from some mean and max values. And we get the mean and max values from plt.xlim. So this tells us the mean and max values that we have on this x-axis. And then we're going to pass these x values to this norm.pdf. And in this case, because we assume that we don't really know the mean and the standard deviation of the true normal distribution that we have, we're going to use the empirical mean and empirical standard deviation. So we just use the data that we have, these 1,000 samples, to find their mean and the standard deviation, and we pass here for this probability density function. And we're going to, at the end, plot this probability density function. So you can see here, now we have our histogram plot, and in the same figure, we have now this probability density function, this bell-shaped curve shown in red for the probability density function of a normal distribution with this mean and this standard deviation. So if you run this, you can see that the mean here is close to 0. So remember here, this is empirical mean, not the true mean of the data. Therefore, we may not exactly get 0, but we would say that this is close enough. And then for the standard deviation, we expect that to get something close to 1, which is 0.97. Obviously, if you want to get better and better estimates, you can always increase the sample size. So for example, here you can increase that to be 10,000. You can see that now we get something that really looks like the PDF for normal distribution. And if I look at the standard deviation of this new data with 10,000 samples in it, you can see that, yes, it is really close to 1. And for the mean, it should be very close to 0, which it is, right? So it's negative 0.002. And this shows very easily here that you can see that we get something very close to the ideal probability density function of the original normal distribution. So in this video, we covered multiple types of plots using matplotlib, line plot, scatter plot, histogram plot, and so on. And I hope you found this video helpful.